Welcome to the lecture on psychometrics. So far, we've dealt with air as if it's an ideal gas. So if we wanted to, say, calculate the density of air, the mass per unit volume, we would use the ideal gas law. PV equals MRT. Rearrange it to look like mass over volume. That would be P over RT. If we wanted the, say, the enthalpy or internal energy of air, we would go to table A17, where the first column is temperature, second column is enthalpy. So the enthalpy of that air only depends on its temperature, or its internal energy only depends on its temperature. This is true when there's no phase change. However, forget all that. There really is a phase change a lot of times when we deal with heating and cooling of air, especially with cooling of air. And so we need to be able to account for that. And that's what we use the psychometric chart for. So first thing we'll do is go over the different properties that we can find on this chart. I'll show you each one of those individually. And then we'll go through the various psychometric processes, which are simple heating, simple cooling, cooling with dehumidification, cooling with dehumidification and reheating, mixing of two air streams, evaporative cooling. Those are the main ones. So let's look at the properties that are on this psychometric chart. Vertical lines go all the way from the bottom to the top of the page. Our dry bulb temperature. Dry bulb just means that's the temperature that you would measure if you had a thermometer or thermocouple or something and you measured the air temperature. So here's 30 degrees C. This goes all the way straight up to the top of the page. So 30 degrees, there's a line of 30 degrees. Horizontal lines are lines of constant humidity ratio. So that is the grams of water, vapor that's in the air, per kilogram of air. So here you see the units of it, and I'll just pick 10. So here's 10 grams per kilogram. Horizontal line all the way across the page. So those are in red. Let's do black lines of relative humidity. So relative humidity tells us how close we are to saturation. This line right here, 100% relative humidity, is called the saturation line. So based on the temperature of air, and I should point out this psychometric chart is for atmospheric pressure, sea level. Say our air is cold, down here at 5 degrees C. It won't support much moisture. So the humidity ratio at 100% relative humidity is relatively low. So the humidity ratio there is less than 6, maybe 5.5. Where if our temperature is higher, say our temperature is 30 degrees, at 100% relative humidity, our humidity ratio is way up here around 28. So that warm air will support much more moisture. And so the relative humidity just tells you how close you are to saturation at your given temperature. So for example, if I'm at 15 degrees and I have this humidity ratio, this much, say 5, maybe just over 5 grams per kilogram of air, that's about half of, 50% of the moisture that, the amount of moisture that air at 15 degrees can hold. Here's the maximum, and I'm 50% of the way from no humidity to 100% humidity. So one way to see this distance is, this is equal to that. Really the other way is to look on this curve here. Here's 50% relative humidity. So here's where it tells you the relative humidities all the way up. All right, let's use a highlighter here for lines of constant enthalpy. So way over here are enthalpies. And if I just pick, 60 kilojoules per kilogram, that line goes all the way down here. So this is a really important thing to note. In table A17, temperature and humidity fell right on top of one another. They were, if you knew the temperature, you knew the enthalpy. Here, lines of constant enthalpy are doing this. So if we're at 30 degrees, our enthalpy might be 30 kilojoules per kilogram if we had no humidity here. Or it might be 100 kilojoules per kilogram if we had 100% relative humidity. So the amount of moisture in the air affects the enthalpy of that air. Let's see, I'm out of color, so I'm going to go back to blue. Specific volumes have this steeper slope than the enthalpy. So enthalpies have this slope, specific volumes have these slopes. So there's 0.92 cubic meters per kilogram, and then there's an unmarked one, and then there's 0.9, unmarked, 0.88, all the way down. So you can see the colder air is more dense, has a lower specific volume, greater, say, humidity. You've got higher specific volumes also. Let's see what else is on here that's important. Parallel to the lines of enthalpy, or very close to parallel, are these dotted lines. These are called wet bulb temperature. So here's one, it goes down this way. It's an unmarked one. They only mark every 5 wet bulb temperature. So here's 25 degree wet bulb temperature. What that is if you started evaporating water into the air and you did it adiabatically. You weren't adding or taking away any moisture, you were only evaporating water into the air. The temperature of that air would decrease, the energy would go into the phase change to change the phase there. And so it's the temperature that you could lower the temperature of air to at 100% relative humidity. So say I started out, I don't know, we'll just say at this point with, what's that, 20% relative humidity, roughly 44 degrees, something like that, 44 and a half. If I started evaporating water into the air, the humidity ratio would go up and the temperature would go down along this line that I'm putting here until I hit 100% saturated, which is going to be 25 degrees. So the wet bulb temperature 25, when I hit here, if I drop straight down, that's also going to be 25, because at saturation, the wet bulb temperature and the dry bulb temperature are the same thing. You can't evaporate any more water into the air, so you can't lower its temperature anymore. So if you have dry air, the wet bulb temperature will be much less than the dry bulb temperature. You kind of experience that. Say you go to a place that's very humid and you go swimming, you get out of the pool, it doesn't change much. It feels pretty much the same. Or if you go somewhere really dry, say you go to Las Vegas and you lose all your money, you go to the pool and get out of the pool, it feels extremely cold. Even if it's 105 degrees outside, that evaporation is happening really quickly. The temperature on your skin goes to the wet bulb temperature, which might be very different. Say it's 10% relative humidity, 40 degrees C, which is about 100 Fahrenheit. As that water evaporates, we're on, let's see, here's 20, 25, 24, 23, 22, 21, 20, 19. We're about 19 degrees C. So here's 20, I've kind of written over it, but that's the wet bulb temperature of 20. There's the wet bulb temperature of 19. So we would have a wet bulb temperature less than 19 degrees C. That's in the 60s Fahrenheit. So big difference. I think those are the main properties that we have on here. So I'll make a new video for the different psychometric processes.